Hey guys. Um, yeah, so this tutorial is hands-on, so if you please take up your laptop, that will be great. I remember they ask you to have Anaconda, so I'll try to work with that, even though I don't use it, but okay, let's see how it goes. So for those that will follow, I will tell you some installation really fast of the OpenCV. It should take about 2 minutes, and then I will introduce myself. In the meantime, it should be installing. So let's do this. So if you can please go to that repository and in GitHub Agundez Pydata. That will be great. So let me do it also me. Yep. So just more or less. Let's see if it loads. If not, basically. OK, so installation steps. It's going to be one command. Huh? Don't be scared. OK, so now this one. Conda install, basically. OK. So normally OpenCV, for have all the functionalities of OpenCV, you need to compile it from the binaries. But for this tutorial, you're not going to be able to follow just a really small part if you use Conda. But for everything else, you will be able. For the interesting parts, you will be able to do it. So OK, let's try it. Oh, please, first I need to make sure. Okie dokie. So my name is Rodrigo, and I'm from Mexico. And I study physics, and I did my PhD here in the Netherlands in theoretical physics and quantum mechanics. And I recently started as a data scientist in quality. So let's see. And I've been using this tool a bit for fun. We also have a live demo there in the stand. You like to compares you to some famous stars. So I normally get Mr. Bean, but maybe you get Brad Pitt or something. I don't know. OK, so let's proceed here. You probably did this already. So let's see. OK, so for OpenCV, if you later want to use it, so there are, of course, many versions. But normally, you can do 3.0, 3.1. And when you try to do face recognition, I will try to address those two. Just to we're going to use 3.1. But 3.0 has, it breaks. It is quite different when you do recognition. So just keep in mind if later in your house you want to just play with it. OK, so it's going pretty slow, of course. But the good thing is I already have it here, compiled, of course, for myself. So let's see. So just make sure, of course, when you do it, just make sure if you can import this, that face, then you're ready to go. You basically have everything. Because you have OpenCV has CV2, and then it has the normal packages. But for face recognition and machine learning techniques, face recognition, you do CV2.face. And if you do that, then 3.1. Perfect. And the other one is still, pretty slow. OK, so, OK. Hopefully, you guys will do it a bit faster. Is somebody already got it? No? More or less? 50%? Something like that? So I will help you. OK. So let's see. So a live demo, that's dangerous stuff. Okie dokie. So I hope it doesn't take that much time. OK, so later if you want to use the notebooks, and I also made an application within that you can also in the repository where you can use these. We're going to use 3 different methods to recognize faces. And you can use it and look at the code and change stuff, whatever. That's pretty nice. And of course, the notebooks are available. And we'll talk about, so I will do this thing. OK, but I will also try to explain you how it works a little bit. Because, well, it is some linear algebra. And say, in quantum mechanics, there's a lot, so I like it. And OK, so I'm going to start okay. So, okay. So, oh, the clicker, yeah, of course. So a bit about OpenCV. It's an open source computer vision machine learning software library, and it has wrapper for Python. It's writing in C++ originally, so it works quite fast, in my opinion. And you have many different recognizers for face, already trained models for face, for faces, for legs, for a person. So there you can look like in YouTube, for example, and do OpenCV, and there's people that put it in their car already, of course, with some extra nicely features. And they already detect the people like going through a zebra walk, or that's pretty nice. Okay, and of course, if you get a really nice camera, well, of course, it works even better. With this camera, well, maybe not. Okay, so, okay, let's see. Okay, so through this tutorial, we'll first learn the basics. So I will try to do there are other libraries that you can do this, but I will try to do everything with OpenCV. And we'll first learn how to manipulate some of the basics of images and videos. And then we'll create something with it, very small, but something. And then we'll learn how to do the face detection through OpenCV. And we're going to build our data set. So let's see how that goes. So I'm going to need a volunteer for that. Because, of course, if it's only myself, it's, of course, going to recognize me. So maybe Marcel can help me, or anyone. It's also good. OK, and then, then we will build a model using OpenCV. And this here is going to be different for 3.0, 3.1. And then we will try to recognize the faces in a live video feed. And then I guess we will have time, because now I think I have an hour and a half, so it's pretty. We'll try to do a classification, having the knowledge of what the eigenvectors are in linear algebra. So we will try to classify other type of objects, like, for example, I think what we will try to do, and I just did it yesterday, so don't expect too much, but the theory is there. Some heart disease data, where they're classified as the cancer is benign, or in Spanish, maligno. I don't know the other. Yeah, like bad or good. I don't know they work. Anyway, so we'll try to do it. And OK, I hope more or less. OK, so we're going to import NumPy, of course. This CV2, this is just to output the version. Okie doke. Perfect. OK. And of course, I import CV2, and then the CV2 version is just to check, just to double check. Because before I had 3.0, and then I need to change things, and I needed to know which notebook was what. So. OK. OK, so we're going to start with the basics. So we're going to take a picture. Pretty simple. So for this, we'd use the video capture. And for this, you just send an index, 0, 1, 2. If you have 1 camera, 2 cameras, the webcam, doesn't matter. You have 5, 6, doesn't matter. It will just create an object of basically webcam. And then you can read from this webcam, and it's basically what it takes as a frame. So, and then it returns if it actually read it or not. And of course, the frame. And here I will print just in case it doesn't work. And then the last command, OK? The last command is actually very important, because if you forget to release it, and trust me, it's really annoying, and then you close your application, your camera will still be on, but you cannot. There's no way for you to close it but to basically log out and log in, or kill it like from the process. So it's really annoying. So don't forget that command when you actually do an application, because here is not really a problem. When you create an application, if it crashes and it didn't get to that command, it's not good. OK. OK, we took the picture. Yeah, but where is this, right? OK, so OpenCV has its own thing to show your pictures, and for this it shows like an external window. And for this, because the external window is interactive, let's say we have to open another thread that OpenCV already provides you, so we can handle whatever events happen in the window without stopping the events in the notebook. But normally you wouldn't have, like if you do an application, and if you want something to be running at the same time, of course the window is running, then you do it. But if not, there's no reason to do it. OK, and very easy. So we declare basically a window here, this one. And I just call it Pydata tutorial. And then you send a flag. In this case, you just say window normal. And it just opens. Ooh. Anyway, so that's a picture, pretty bad one. Okay, anyway. So, and basically you can just, normal means that you can expand it or stuff, doesn't really matter. And if you don't open the start window thread and you close this, your notebook will crash. And then you have to start over. So don't forget the thread. Okay. Okay, and then CV, the wait key just waits for you to open, to just hit a key, and then it close it. And I really like this command, like when they are written like this, destroy all windows. That's pretty, yeah, I really like it. Okay. Okay, so I am show it basically, you just send the frame that you just took, right? And then you send the same name of the window. And then that's it. You can also do, for example, oh, actually, I think I have it here. Yeah, you can also do this. So remember, this is just the basics. And this is basically then the outer size. So now I cannot make it anymore and move it or anything. But anyway, but it's the same thing, the same idea, right? Okay, so let's continue. And please, any questions, whatever, I'm really open for you to interrupt me, please. Because an hour and a half is too much, so if you interrupt me, it'll be good. Okay, so what about within the notebook, right? Because, well, if you're using the notebook, like, let's use it. Okay, well, the good thing is the frame is a NumPy array. That's great. And it's great also because we can use it, of course, in the notebook, but it's also very good for other stuff, right? Because now you can use basically everything on this. And it's just, well, makes it good. So, of course, we can use just matplotlib and then display it there. And, of course, it plays it like a graph, so that's pretty awful. And I think I cannot really see the difference. But let me just, maybe if I just do it again, this takes a better one. Okay. Yeah, anyway, you see my hair is like a little weird. It's like blue and then something really strange there happening. And then, okay, so it's because OpenCV, I have no idea why they use BGR instead of RGB. Yeah, it's quite annoying, but, well, you cannot do anything about it. So that's why it looks so bad. So for that, OpenCV also provides this type of functions, CV2, CVT color, and you can change from gray to BGR to RGB to grayscale to HSV to also RGB, and then the other thing for transparency. Yeah, you can basically anything. Probably it's me. Okay, and now we just make it a bit better, right? Now it's the right color, so it's red, how it should be. And then it ticks off, so okay. Anyway, so continue. Okay, read and write images. Okay, so for read and write images, we just do I am write and I am read. Pretty simple. And then you just send the path and NumPy array. And then if you want these, the flags here, if it's 1, 0, or -1, depends if you want to read it in color, in grayscale, or just unchanged if it has an alpha channel. So that's transparency. Okay. So now, okay, well, if OpenCV gets it right in GBR, does it save it in BGR? Because, well, that would be really sucky. And, well, it doesn't. That's a good thing, right? So you can see here, yeah, so the GBR, that's the one from OpenCV. It's quite, well, it's the right colors. And then, of course, for reading, the same thing. You can just do it again. Right? And so within, you can see here that because I changed it, right, it changed this one, but this is the correct one, so in RGB. So within OpenCV, everything is right, so don't worry about it. Once you dump it in a file or whatever, it comes back to the normal way. So it's just within it, so you don't have to worry about it. Okay. Is somebody following? No, not really? Oh, okay, cool. Oh, that's great. Okay, yeah, if not, I go a bit slower because I think it's important. It's a tutorial, right? Okay, so anyway, so this is what I was saying. So within OpenCV, yeah, you get it sent in GBR, but like the images and everything is perfectly correct, so don't worry about it. Okay, so this is a useful function when I use to just define, just to print inside the notebook. Pretty useful because I don't want to write that. And then we can also send a title, so, right? And then here, in case the image is in grayscale, it automatically will put it in grayscale. Okay, let's see, what else do we have? Okay, dokie. Okay, so now let's start taking a video, right? So it gets, okay. So I don't know about this light, but anyway, yeah, we'll see. Maybe this way will be better. Yeah, maybe, I don't know. Okay, so let's see. So it's the same thing, but now we don't release it, right? So it's there, it's capturing. And of course, then I make this command just to see if it handles it, because yeah, it's pretty useful. Right now, of course, it makes no difference. It's a bit to put it there doesn't make sense. But then to give a feedback, because then, like I said, sometimes it's open because something crashed. So it's good to have a print that we implement in a class later. Okay. So again, the same thing. Oh, so that's the whole idea, right? You will take a frame, you show it, you repeat, you show it, you repeat, of course, and then you get a video. Okay, so the same stuff. So we open again a window, and then we just do a loop, and then we use this useful command of wait key, and then those are in milliseconds, so 20 milliseconds it waits for pressing you a key, and then it just basically renews the window. And let's see what happens here. Yeah, so that's me. Hello. Okay, and anyway, okay. Oh yeah, much better lighting. Very good. Okay. So now that weird thing that is there, I don't know if you know what it is. No? That the 0 times FF. But it's to convert it in order to have the escape, because escape is 27 for if you want to just have a key instead of any key. Before it was just any key, now it's escape. And then we will use it for other letters, but right now it's just like that. Okay, so you see I didn't send release. So if somebody is following, you will see that your camera is still on, and this is what I mean. Okay, so we continue using it because it's on. I didn't need to open again. Okay, now we do it just within the notebook. And with the notebook, we use this useful function clear output. Right? I hope you know it, but if not, you just clear output and you say that the wait true, so it waits for the new output in order to replace it. So it's pretty simple. Okie dokie. Okay, and then don't forget that. Yeah, of course. I'm pretty sure if I don't put it there, I will forget it. So good thing I put it there. Okay. What is? Ooh, it's not releasing. You see? Why not? Oh yeah. Oh yeah, of course, yeah, this is still running, and I put a keyboard interrupt because there's a difference from the window where you can catch pressing a key. The notebook is always running, so if I press a key, that basically doesn't catch it, because so what I do is just the keyboard interrupt. So in the notebook, you would just go to the other mode and double I, and then basically that's it, keyboard interrupt. And if you don't do that, again, if you just close it, the camera is still on, and then gives you this problem, so it's important to catch it. Okay, so we continue. Okay, read and write videos. Okay, so similar to the images, now you have this video writer 4CC, and that's what defines the codecs that you're going to use for your video. So if you're shooting a video in your house, or you're shooting a video, surveillance video or something, I don't know, and you want to save it, so this defines. I will go a little bit over what this is in the next slide. And then you define basically a container. And this container, we're going to put all your frames as fast as you want. And then you're basically going to dump that container basically into a file. Okay, so for the 4CC, you can define all these type of things like XVIT, MGPG, X26, and for all the different, you can go to this web page, and then there has a full list of all the codecs that you can use. And, okay, so let's see. Okay, so now, I do this video capture, and I already have saved a video for testing. And it's an AVI video, and if you see this video capture, can also the index, but it can also you just send a path to your video. Okay, and then it saves in the same way as it was the camera, and then I print the video is open just to make sure it's working. And then the same thing about naming the window. You can also resize it, as I do here. And then we do exactly the same stuff. And if you see here, I changed this just to now for Q. So now you can use it later for if you want to change, let's say, I will use it a bit later. So you can catch different keys if you want to have different functionalities, or you may make a game, and then you would have these keys to move it around. Okay, and so basically, let's see this video. So I don't remember what was this video about. Oh yeah, so this guy that annoys the cat. I found it pretty funny. But I don't know if you've seen it. Have you seen it? I don't know. But then the cat goes, and it's pretty funny, his reaction later. Yeah, but the guys, it's just, anyway. So if you see, the video is gonna finish, and my notebook is gonna crash, basically. Let's see, and that's because it's trying to read every time, right? You can see that. It's trying to read, so it tried to read, but there's nothing to read anymore because the video finished, right? So for that, we can use this here, of course, that we mentioned at the beginning, this one. And you can also, of course, change the frames within the thing here. So it provides you all again. So now we change it to grayscale. And now we're going to flip it also. You can do many other stuff. So let's see what how this works. Yeah. So it's grayscale. It got flipped. And now it should finish, of course. And it's gonna crash because we're using this feedback from, this called RRT. Well, we can let it finish, but do you want to laugh again? I don't know. Anyway, so let's let it finish, just to see it won't crash or anything. Okay, and then in the next one, we will do it within the notebook, but then we'll do something to the video. So it didn't crash, everything good, perfect. Okay, so now what we're gonna do here, we can also, of course, it's a NumPy array, so then we could cut half of it, or in this case, I think I'd throw a third of it, because, yeah, go ahead, sorry.
Have you ever used the CUDA library to do the video encoding using
No.
a GPU?
Yeah. Okay. So anyway, so let's just cut 1/3 of it, and then, of course, makes it much better. I mean, pretty simple stuff. Okay, and then we will, let's see. Oh, yeah, so keyboard interrupt, the same stuff. If you see the videos in the notebook, of course, are much slower. Okay, so now we're gonna record a video. In OpenCV, more or less, I advise you to use this rule, more or less. So because you have to give the frames per second. So when you use this key weight in the milliseconds, you use this formula, and then your video will be more or less as a real-time movement. So let's see, more or less. So I think it's taking a video of me. Yeah, of course. And then let's display it. Where is it? Yeah, perfect. Okay, so now it's the video before. So very simple, very easy. So you want to do that stuff. Okay, so one of the things, so this I use AVI, of course. And of course, the same thing for this. Oh yeah, okay, here. And then here. Yeah, if you see, I put 40 milliseconds, and then I use that rule in order to send the frames per second. So more or less, it will be 45, right? But so that works. Oh, sorry, 50. Okay. So we can do the same thing, of course. Then we do that. Then we do this, and of course, it works and everything. Okay, now, just in case, I'm gonna give you a tip, just in case, probably you know, but okay. So if you try, for example, that video that I just recorded with AVI, if you try to put it in HTML, of course, it's not gonna work, right? And that's it, just like a tip. It doesn't work because, well, these things here. Because, well, basically MP4 will be the way to go. And that's why if you want to do that and then use it in your web page or use it somewhere else, I don't know, you can encode it with this one, the H.264, and then the container in MP4. And if I do that, then I just close it. Okay, and I go there. So here it is, of course. Oh, okay. So it captures all the, yeah, it captures all the images. And for example, if you go online and try to convert this AVI to MP4, I don't know why they don't work well. So now, if you want to implement this in a web page, you probably get a lot of hits just to convert videos, because they don't work very well. Okay, so you can also have a lot of things to write and to draw in an image or in a video. You have create a line, a rectangle, a circle, an ellipse, or just put text in it. And of course, so this I will just demonstrate something really quick. So you just put a rectangle, right? And then if you want, just anyway. So pretty easy, nothing complicated about this. Okay, pretty good. And that's basically just put text, you send the coordinates and stuff. And the rectangle is the same thing, just the coordinates of both. But it's basically using the same thing. Okay, now this thing, we're going to use a mask now. We're going to work a little bit with it. I don't know if you're familiar with the concept of a mask, or if you maybe have some work before in semiconductors, where they use it to do basically the chips and the wafers, or if you're a graffiti artist, where you also use a mask. Yeah, so anyway, so let's go and use it. Okay, so in this case, what I do is here I create this circle in the mask, so the mask is completely black, and then I create this circle in a white color. So then imagine just it's a circle white, and then everything else is black. And then by doing a bitwise operation over my actual frame in the mask, then you get, of course, this thing where everything blocks. So wherever you put the white on it, well, of course, let it pass, and that's what a mask does. Okay, so let's continue. Okay, so now handling mouse events. Like I said, if you want to make interactive window, you can also set like a mouse callback, where you send the name of the window that you define, and then just the callback function, basically, and then you define the function, of course. And it has all kinds of things, like all for the mouse, left button, down, scroll, and this is just a few. I didn't even put them all. So you can already, if you want to create kind of a paint or something like that, or even better, you can go ahead and do it. It gives you all the controls. Okay, so what I'm going to do here is basically I create a mask. I believe, oh no, I just create circles with my mouse, so nothing special, where I basically just define the coordinates. Oh, that's the first. So let's say you just define like coordinates and stuff by sending this circle and then just graph the events. But then you can use whatever you want, right, for this. Okay, so let's continue. And then something maybe you want to build something for kids or something. So you have a video there, and oh, they discover the image behind, right? You're like, oh yeah, hey, I'm there or something. Yeah, you can do a square, of course, and stuff like that, and whatever. And then of course, if you do the CV2K for another letter, then you can change between whatever you want and stuff. I mean, it's not okay. So let's see. Okay. Well, okay. So that was basically some basic manipulation of the things. So now we will go to basically face detection, and this is basically the images that the functions that I did that we did in the previous notebook. So it's nothing normal. So I'll try to go quite fast on this. So okay. Okay, so the face detection using hard feature-based cascade filters. So this is what the OpenCV uses to detect faces. I don't know if some of you have heard of this algorithm before. Yeah, okay, so I'll try to go really fast with it. Okay, so the hard features are all these squares that you can see here, right? And then you can rotate them or whatever. It just goes through the image, and then they enlarge them, rectangles the other way around, and it just goes inside. And what it does, it subtracts whatever the sum of the pixel intensity in the white, the black subtracts to the white. And then it gets you an output, and in this way it recognizes some of the features. For example, that the cavity of the eyes is darker than the nose, and then also that the forehead normally is, that the cheekbones are a bit, have more light normally than the eyes, and all these kind of features. And this is basically what it does. It just tries all of them, Yeah, and it outputs like yeah, whatever the main features are. So now if you do this, for example, even in a 24 by 24 window, and you take all the possibilities of combinations, that gives you 160,000 possible features that you can have. So that's a bit too much. And yeah, and then of course every time you apply one of these, you need to sum all these pixel intensities. So there are different solutions, and one is AdaBoost. The other idea is integral image. And AdaBoost, what it does, oh sorry, integral image first. So normally you will have to subtract all the pixels from the white to the black, right? Or the other way around, sorry. But now instead, so at the beginning you define your image and you do this operation. You take a point here, and then you do C, let's say you do C minus A, sorry, C plus A, B and C, B and D. So for example now, so this is an example here. So now, for example, if I want to know the pixel intensity in this region, right? I don't need to sum. I don't need to sum this anymore. This is equal, of course, to all the region in C, and then plus A minus the region here in B includes all this, and minus D in this. Yeah? So every point is defined as the sum of the pixel intensities to the left and up. And if you do that, then every time you need to sum all these pixels, you basically have to do 4 numbers instead of the whole region. I think it's quite simple and quite clever, but maybe it's just me. OK, so that's basically what you reduce every image to an integral image. And then AdaBoost, so what it does is basically a linear combination. Well, when I learned, AdaBoost, yeah, a linear combination, OK. And then, so you have all these features, and of course, some are more important than others. And it just basically ranks them and selects the best ones that you can use. And then, of course, each of these features becomes a weak classifier, but by doing the linear combination, it creates a strong classifier now, right? OK. And of course, the bigger the alpha, the more relevant the feature is. OK, and then from these, you take around 160,000, and then you can cut it. I think OpenCV, I think, or the Viola Jones uses around 6,000 features. Which are the most important. Okay, so questions? No? Okay, great. Okay, okay. So you still have 6,000 features, and every time you have an image, you have to sweep every feature for every size, right? So it still is a lot, and it will be so slow. So for this, the solution is cascading, and cascading basically is this. So cascading means you separate the features in batches, and then you send certain batch to check to the image, and it says so you go the most robust to the less robust, and then if the first discarded, okay, then throw it away. Don't even check in the other ones, and then the next step. So of course you can use this idea in some other type of machine learning techniques. If you're using different ones, and you know one is like really good one, but then the other one only checks certain part of your data, that you can check just for the first one. Yes, don't even bother for the second one. Just throw it away. Okay, so for this, the OpenCV uses 32 stages, and with 10, 25, and like this, and 50 features. And then by doing all this, OpenCV basically it's able to create a recognizer of the object that you basically train it with. And of course, this idea is not only for faces. I mean, people have used it for bananas, apparently, for cars, for phones, for a hand. I think for dogs also. I've seen also for like fruits. So if you want to train the algorithm for a certain object, just go ahead and do it. OK, so but OpenCV provides you with all of this. So basically, it can detect the eyes with glasses, the left ear, the eye, the front leg, so apparently everything. The right eye, and it has also different ones like upper body and all this kind of stuff. So the one that we're going to use is frontal face underscore the alternative. OK? OK, now. So the detector, you create a detector by passing the cascade classifier, and you basically pass one of these ones, whatever you want, to create the object. And then basically what it does, then the detector just basically detects and you pass the image, and you pass certain, like the scale factor, the minimum neighbors, minimum size, and flags. The scale factor means how much do you want. So because it's checking and then reducing and stuff, is how much do you want it to grow or get little stuff. So the recommended factor is 1.2. If you do like 1.1, it gets a bit slow. And the minimum neighbors is, of course, how many neighbors have to flag positive in order to recognize the object. OK. And the coordinates is basically x, y, width, and height. That's what it returns. So it tells you, let's say, a square around the object that you found, basically. OK. OK, so let's just, so right now, ooh, this is not going to work, I think. Maybe if I do, it's too bright. I think it's just when the, yeah, I think this will work. When the camera, ooh. Yeah. Okay, better. Just when the camera opens for the first time, it gets like when you wake up and then there's a lot of light. Similar to that. So yeah, so I had to take a picture first so that it open, and then it gets all these lighting, and then it gets it back in the correct way. So let me see if I can maybe this way would be better. OK, let's see if it works. OK, so we have that image, and now we send it to the detector. And then the scale factor 1.2, minimum neighbors, the minimum size, of course, whatever you want. And so we pass this frontal face, or actually rename it, but it's the alternative, the one. And it passed the detector. And the detector just basically detects, and I pass the frame that I just took in the previous slide. And then basically it will, yeah. So it tells me, yeah, OK, you detected one. So it's important to see what happens if it doesn't detect anything, or what happens if it detects one or two or stuff, right? So what it detects, if it detects one, it's a NumPy array, and it gives you basically, if it detects 5, so it's 5 rows of different coordinates. In this case, it's just one. So if I, oh yeah. So let's say I go away. Yeah. So now it returns a tuple. And of course, the length is 0. So if you see, if you can apply, of course, the length to a tuple or to a NumPy array. So you can use this as to differentiate if it used one or if it found something or not. So let's take just to, I think I need it later. Let me see first. OK. OK, so now, like I said, it returned the coordinates. So what I'm going to do is just going to draw a rectangle around my face using the rectangle function. So I just send the coordinates that the same the detection method sent to me, and I just send it to rectangle, and I say, OK, paint a rectangle. Pretty good. And OK, and this is the thickness, and this is basically the color, and then of course the coordinates, and then just the frame where you want to paint it in. And we use the function that we defined before. Pretty good. OK, so we're going to add some helpful definitions because too much typing. OK, so yeah, so we're gonna declare this face detector, and then the function just detect, very easy stuff, and then find the biggest object, and then also this one, which is basically this is the most helpful thing, because then I don't forget it. If it just gets the object gets deleted, it's just this by itself, and then of course captures. So that's pretty helpful stuff. OK. Let's see. So we activate this, then we do that. OK, now we do it within, and now basically it follows me around. It just goes and says, OK, yeah, I found you. I draw the rectangle. I'm sorry? That doesn't work. Yeah, but you can, yeah, if I go here. Yeah, but you can, of course, that's something that yeah, you can work with it, because there's a function that rotates, and you basically rotate it, let's say, 10 degrees every something, and then it will detect it. And then you rotate also the rectangle, and then it goes back. So then basically even if you will be something like that, it will detect it. But it's just rotating the... for that, I think it has certain angle. So for example, let's say you're here, and then maybe a little bit, yeah, it goes away, it goes, so it's not really good. And if I go completely, of course not. But there is one for the ones that I show you, there is one for sides. But then you will have to check, you will have to check double. You will have to create a detector for the front and a detector for the side. Yeah, exactly. There's also a detector for the eyes, for example, so you can use that also. So you can combine a lot of stuff. So for example, for the eyes, it has a lot of false positives. That is used, we'll talk about it later, for alignment. Like if you don't know whether this person is like that or stuff. So if you want to recognize the face, the most important one, for my opinion, one of the most important things is to have a normalized image similar to your database or whatever. And then, of course, you use the eyes to rotate this thing, for example. So pretty helpful. OK, so here I am again. Again, this guy. OK. Oh, yeah. OK, we have learned to detect faces. Yeah, great. OK, so we go. This is basically when you want to do capture faces and then send it to your machine learning algorithm, basically the best thing that you can do is to more or less try to normalize your images. The images that you are going to train it with, and then use the same image normalization for the faces that you're trying to recognize, right? Then it will make your algorithm much better. OK, so the ones that we will do here, we're going to cut the face, we're going to normalize the pixel intensity, and then we're going to resize the face image also. And OK. And if, of course, you talk about state of the art, this is a paper in 2014 from Deep Face. And basically, well, that's awesome, right? They just find so many features in the face, right? You can see, for example, let's say, and then rotates the face. Like if you are facing, like you can see A and G, so it's completely rotated. It's the same face. So it creates the extra part from your skin that you don't have by doing the mirroring, maybe from left and right. It creates the part that you're missing, and then it gets you completely in front. And of course, if they do this, I mean, of course, you get super accuracy. But it's super nice, right? We won't do that. But yeah, but that's like state of the art. And then what they use here, of course, is deep learning. But their images, they're still normalized. OK? OK. Very good. So if you want to check that article, it's pretty nice. OK, so first, we're going to just cut the face, and we're going to get only the 80% of the face, because here the things in the back can be noisy. Of course, if the person has like big ears, that will be a plus, but we're going to cut them. Yeah, well, yeah, I don't know. OK, anyway. OK, so if you see this is the result, just cuts the thing. Oh, maybe I did not do this. OK. Now we're going to normalize the intensity. And for this, it's very easy. It's just this command here, equalize histogram. And then we just normalize the face. And then for here, what I'm doing is just sending a list of faces, of images, and it just returns the list of images, but normalized. OK. And what it does, it tries to use the complete grayscale. And then by doing that, the contrast of your picture will increase, of course, right? Because imagine that then there's a difference between 2 pixels, but it's within certain range of the whole 0 to 255. And then, of course, by extending it, then the difference between those 2 pixels will increase. So that will increase your contrast, and that will make your features of your face, of course, much better. OK. So I think, yeah, so let's see. So for example, this is the picture that I took, the last picture. And then it's the normal one and normalized. So you can see how the features, for example, of the eyes now are much present in the picture. Also of the forehead, for example, is a bit light in here. And, well, the light's not the best, but yeah. So you can see all this kind of stuff that gets emphasized by doing this normalization. You can also normalize the red channel, the blue channel, and the green channel. So that's basically what you do with this stuff. Okay. And this is basically just to compare the histogram. So the blue one is the histogram of the original picture, and the red one is the histogram of the picture later. So you can see how it completely got extended, and then the features, because of this, get more separated, the pixel intensities. So now, of course, it's more prominent things. OK, so this is just basically cutting and normalizing the face, so just to see the result. And then we can do just a resize. Basically, if you have a picture bigger, then here we have different things to make it bigger or smaller, which is the recommended one. And basically, because we want to normalize the dataset, and we just put it 50 by 50. OK, so now this is basically the result of this thing. Right? So this is a 50 by 50. It looks pretty bad, but for the algorithm, I hope will be enough. OK. OK, now the alignment. We won't do the alignment, but I will just going to tell you about it. So for example, for this, you will detect the face, for example, and then send that cut of the face to recognize the eyes. And then once you recognize the eyes, of course, you have the coordinates. And of course, if you just create a rotating matrix for the NumPy array. And then you can rotate this matrix in order that now you have your face aligned, and now you have a nice data set in this case. Yeah. So it also works with the OpenCV, and you can do also the eyes. In this case, we won't do it. It's a bit an overkill for this thing, but yeah. OK, so this is just basically bringing it all together, useful things. Nothing important. OK, so then we're going to build our data set. So we're going to, of course, detect. We're going to cut it, normalize, resize, and save. OK, so now for this, let me see. OK, so I'm going to take of me. So it's just, of course, going to ask my name. And then I used CV write, just to write it in a folder. You can see here. Right? So let's see. And it should take around, how many images? 10 images. OK, even though it says 20. But so let's just wait, 6. And his smile. OK. And then, so who's going to help me? Yeah? Can you? OK. Come on. Yeah, if not, this is too simple. OK, let me just do this. OK, so you have to stand up there. You're probably too tall, but yeah, put your name. Oh, Marcel. Oh, OK, so we'll do that. Yeah, so yeah, get a bit closer, I think. Just the lightning. Go, go, go. Just you have the count in there. Oh, I can see it, of course, there. Oh yeah, let's see. The pictures are not very accurate. But yeah, they're very blurry, but let's see. Let's see. Maybe it works. OK, thank you. OK. OK, let's see. OK, so I guess everything this we've done before. We detect the face here, of course. And then we just we checked it for the length, because, well, if there's no length, we don't want to do anything. I set a timer here, so it takes about, I think, every second or so. Oh, yeah, here I said. And then, of course, the normalized pipeline that we defined, the cutting, the normalizing of the histogram, and the resizing, of course. And then we basically, OK, so we're, OK. OK, so we're done. OK. So now let's build the model. This is the same function that we defined before. I didn't separate the things, because if it breaks, like for the camera thing, I have to start over. So that's why I make separate ones. So sorry. Anyway, so you have 3 options with OpenCV. You have eigenfaces, feature faces, and LBPH, so linear binary patterns. I will try to explain more or less how they work. And they're very simple functions. And what you pass to these things is just basically set an images, and we will see how that works. OK, so eigenfaces. Eigenfaces, what it does is, if you think about an image, let's say 100 by 100, then if you think about each pixel being a dimension, then of course this picture lies in a 10,000 dimensional space. And so of course, perhaps not all dimensions are useful. Well, obviously not. So then it performs basically a PCA, what it basically deconstructs the eigenvectors of these things. And yeah, and only it interprets like only a few dimensions account for the most of the information, right? Okay, and I hope everybody's comfortable with this information. Okay. Yeah, so this is a bit of linear algebra. I don't know. Well, I'll do it very fast. Okay, so the example, let's take a data set of for 400 images. And then, of course, if what you want to create is this product here, right? But then you have a problem, right? Because, well, you can see the size of the matrix. But instead, you can, for linear algebra, you can take basically this opposite, let's call it opposite product instead, right? And then you can recover the original eigenvector by multiplying by the initial matrix. And this is like a nice game, well, a nice trick in order to not have to compute this thing, all these eigenvectors of this gigantic matrix. And this one that you compute the eigenvectors of is basically a 400 by 400, right? Because you have the transpose of it. So, okay, sorry, that was more or less. It's a trick. So you can use it also for other stuff, right? If you have a matrix that you want to find the PCA or the eigenvectors or all this kind of stuff, you can use that trick. Basically, many of the libraries use this trick, but just in the back. Okay, okay, and then of course it projects the eigenvectors projects all the samples in the PCA subspace, and then projects also the sample in the PCA subspace, and then calculates the difference in that subspace, like. With all the images. In the image that is the closest one, because you gave a label before, that flags like that's label. Okay, flag it like that. So imagine it, yeah, well, imagine like hyperdimensional space, and then you have one point in the other, and you have all this, or your training, all the pictures from your training data, and they're around there somewhere, and then you have the sample here, and then it calculates the distance just by basically just with the vector distance. And then basically that's it. It flags the closest one. Okay, so if you see, you've seen this I think many times, but this is the reconstruction of a face, just getting more eigenvectors, right? And you can see, well, that not all of them are necessary, of course. I think you've seen this before. But then the problem with eigenvectors, it encodes a lot of the illumination, right? And then because it does not group the eigenvectors in different like in different labels. It just puts them all in the same space. It regards which features are important for each group, right? What it does, it identifies the features for all groups, for all labels. And then by doing that, then it's just, of course, if you have certain light in certain amount of pictures, it doesn't mean that is useful for the algorithm will be useful information because that's what defines maybe your data set, and it will use it. Okay. Okay, the other one is feature faces. And this uses linear discriminant analysis, and it basically was proposed in 1936. And this is a little bit different, so it groups them first. It groups the labels first, and then once they're grouped, it tries to identify the features that are important for each group. Not for not for all of them, but just for each group the features. And then it tries to, when you send a sample picture, it tries these features specifically for that specific group. And then you can, of course, it will be much more accurate, right, than the one before. Yeah, and it removes like the variance from light, for example. Okay. Oh yeah, let's hear what I just explained. Okay, so it uses, it uses some other, it uses, of course, the dimensionality reduction, but then the features are per class. Okay, so it's a bit more difficult to see because now they are dependent on the class that they belong to, but it gives you an idea more or less. And this is basically the eigenvectors, and this is basically the reconstruction, like if you would do it in the same way of the eigenfaces. And now this is basically a benchmark for performance, but where it uses an AT&T phase database that you can just find online if you want to try your own. Maybe if you do something with deep learning or something, right? Okay. Okay, and this is what the eigenface of, the AT&T database looks like. So it's pretty, yeah, it's pretty common, pretty easy to. If you do this with a really high accuracy, okay, you're ready to go to the next one. That is basically identifying faces in the wild, and that's what the deep face does. So it can be like a stadium or a crowd, it doesn't really matter, or there's like behind a window or something, and it recognizes them. So if you deal with this and it works very well, then switch to the faces in the wild. Just if you type that. So the next one is the LBPH faces. Okay. So what this has is don't look at the whole image, but then look at patterns inside, like specific places of the image. And then what it does, basically, you get the pixel in the middle, and then you create a threshold for all the other ones. Right? If it's bigger, you flag it as a 1. If it's smaller, you flag it as a 0. Right? You can see here. Right? And then you turn that binary number into a decimal. And then you assign, instead of assigning, let's say, that pixel, you assign that decimal that corresponds to that binary number. And by doing that, you can identify certain patterns on the image that were not recognized before by the other ones. And what it does, for example, it does this kind of feature, a circle feature identification, if you will call it. So, for example, a line, an edge, a corner, a spot. This is the basic ones. And, sorry. Yeah, and then this is, for example, this is the example of pictures, right? And then by applying the local binary parents, it turns into this. So pretty weird, but. Okay. And it's pretty robust, as you can see, against this kind of lightning. Like if you have a different lightning, because, well, you see most of them look basically the same. And if you compare this one with this one, well, it's completely different, right? Okay. Okay, so let's so this is a function that just goes to the pictures that we just saved and just puts them in a, basically an array of pictures. So that's it. And now for the recognizer, just call train, you send those pictures and labels. So you send, okay, this picture is for this label, and this picture is for that, stuff like that. Okay. Okay, let's train the models. Okay, pretty fast. Well, there were only 20 pictures, but they're pretty fast. Anyway, so the models were trained. If you see, I just create the object, and it just send the images and labels, and that's it. I'll do it again, just to make sure. Okay, so making a prediction. So if you're using 3.1, you have to create a what is called this collector, and then send the collector, and then from the collector you get the confidence, and you get the prediction. From 3.0, it's much easier. I don't know what, well, probably they changed it for a reason, but you can just do it like this. And actually, I had a bit of a problem because it broke, and I didn't know why, and then I had to really look at the documentation. And the documentation is not really, about 3.1 in Python is not really, documentation not so good, I will say. So it took me some time to figure out that was the problem. So you have to do that. Okay. So let's get a sample picture. Let's hope this works. Okay. So that's my picture. That's my sample. Okay, so now we'll try to recognize that picture that I just took with the pictures that we just trained. And with the 3 algorithms, with the Fisher faces, with the eigenfaces, with the LBPH. And let's see. I think, okay, good. So it did well. Okay, yeah. Okay, now confidence. What about this confidence? What does this number mean? Because it is not a kind of a percentage of how confident I am. The confidence is actually the distance to the vector, yeah, in that high dimensional space. And yeah, normally the LBPH actually that's not exactly it's the distance to the features that are in this high dimensional space that correspond to that class that that it designed by this selecting the most prominent features. Okay, so that went well. Okay, so the last one won't hold you much more. So it's the same features that we have, same functions that we designed before. Okay. Okay, so now let's try to do in a video, and let's see how it works. Okay, so we're gonna try to how to detect faces, normalize them. We're gonna train them. We already done that. So recognize faces in a live video feed applies to. So this is me with my girlfriend and the commercial or the discount guys. That you can. I use the application that I made that you can freely use. And yeah, if you want to do for something else, doesn't matter. I don't care. Okay. Anyway. Okay. Let's see here. Okay. Yeah, so now I trained them again because, well, it's a new notebook. And now we're going to call the camera. And let's see. So, okay. So now basically what I do here is just the same thing, but it's inside like the functions. So to take the prediction out and then just draw a rectangle. And I believe I put the name of whatever the recognized person is. So Marcel, is it possible that you come here? Okay, so that's me, and I hope it works. Yeah, okay. Maybe it also does too. Yeah, it did work, so. Yeah. Yeah, we're so similar. It's just. Yeah, of course. Anyway, it went pretty well. I had to stand like in my toes or something. Okay, pretty good. So let's see how we. Okay. So we have a bit more. Okay, so like I told you, now we're going to set a threshold here. And then the threshold, basically, I'm going to use, I believe, LBPH. And the threshold, more or less, is by trial and error. I cannot really tell you how much it will work. But if you put it in a condition, by training and more or less looking around, more or less, I think 140. If someone really different comes, it will flag it. I would need the help of some other person. Yeah, you're too similar, but let's see. let's see what happens. Okay, let's see. Okay. So maybe let's see. Yeah. Just come here. Nice. Oh no, you see, it's too similar to Marcel. Come closer. Yeah. Okay. Yeah, so it does work. So the threshold is more or less trial and error. If I put it maybe lower, it would be better because it was flagging as Marcel. Okay, and then, okay. Now, of course, this won't really be, let's see. Okay, so now if you see, I just changed basically to number 1, right? And now it's, let's see, maybe I need to change maybe. Hey, didn't detect Marcel. Come on. Anyway. All right, someone looks like me, apparently. Anyway, let's see what it does. If I go here. The light maybe, huh? Yeah, it's fine. Doesn't recognize his daddy. Okay, anyway. Okay. Don't be scared. I'm not taking pictures or anything. Okay, so if you think about it, well, you can do a lot of stuff with this. Oh, yeah. Okay. And then, of course, when I do this, that is very helpful. Then also define this function that is basically that's recognition. That's his own stuff. And then, hopefully, this will work. Yeah, so now we're going to do with different threads. And in one thread, we're going to use one camera. And the other thread, we're going to use the other camera. If somebody has another one, I can just use another one. And then, of course, you can do maybe a whole image, something like that. So, of course, you can think about basically a surveillance thing. Or you can install maybe one in your, I don't know, if you have a children and you want to put it in your house and you want to see if he comes near the door or something like that, right? And it can flag, right? Because you can recognize the objects. So that's pretty good. And you can basically plug in whatever you want, and that will work. Okay. No, not to you. Man. Anyway, okay. So almost, yeah. Oh, let me just go back. Okay. Okay. And thank you very. Oh, I have to show you the other one, but we have time. Okay, so anyway, that was basically, I thought didn't have time, but okay. Let's go to do this thing with the data of the heart. Let's see how that works. I have no idea. That basically is notebook 5. Okay, let's see. Oh, this thing still. Okay, so we're going to use pandas for this, of course. Okay, so let's import this thing. Okay, so now this data, it has 32 columns, but the first column is basically an ID of the entrance, whatever, like if it was a database. And the second ID is basically if it's benign or bad, malignant. Yeah, you see? I began with an M, so I knew it, but didn't get it. Okay. So it's basically the data set. And so it has 569 entrants of the data. And then what I do is just collect basically the labels. That was, like I told you, the second column, because, Python starts counting from 0. And I drop the first 2 because they're not important. And then I basically add some, I print here the labels just to see more or less what is in there. So these are the labels. And this is more or less the proportion. So 357. So by doing these value counts, I think you know that. But okay, 357 benign and 212 Jesus, malign. Okay. I'm sorry. Okay, so what I'm going to do here, that I don't know if it's actually good or not. So I'm going to normalize all the entrances, like if they were pixels, from 0 to 255. That is very similar what you do when you have like different features that have different scales, right? Because I don't really, look, I took this data set because from the I don't remember, CUI website or something like this, because it didn't have missing values. They didn't have to lose time in reshaping the data. So I just grabbed the first one that it said no missing values and around nice amount of features. So that's why I grab it. I have no idea what they are. Okay, so by doing that, we basically do what normally is done to normalize it, but instead we're just going to 255. And then let's see. I really don't know how this will perform. Huh? Really have no idea. Okay. I'm not in the presentation. Okay. So now, of course, I'm going to take a random sample to train my algorithm. And basically, then I take my validation data frame here. Okay, and then let's see the proportion. Okay, so I take 400, and the proportion, it's more or less 62%. So I hope it performs better than 62%. I really don't know. Sometimes it does, sometimes it doesn't. Okay, so let's see. So then what I do, I'm not in the presentation mode. Come on. Here. Okay. Okay, so now what I do is, so I have this string of 30 characters, 30 features, right? And then, let's put it back like if it was an image, like we took. So let's reshape it for 6 to 5, right? And that will reshape as if it was an image. And then what I'm going to do then, also for the training and the validation one. Okay. And then basically what I'm going to show change, because it also receives as a label only numbers like 0 and 1. So I'm going to put 1, of course, to the malign and benign, to the 0. So just changing that. And I'm going to just open the eigenface recognizer. Why this one? I don't know, but let's just do this one. And then you can set here the number of components, but I'm just going to choose 10. That means the number of eigenvectors that you're going to use. And then we're going to train it. Okay? And then here it goes. So now we're going to call the collector, and then I'm going to go and try to identify with all the validation data. And then we're going to see which ones got correctly, and then just going to make a counter. And then I'm going to make the proportion. I have no idea. Probably, I hope it doesn't do that bad. So here it goes. Yeah, not so good. Not so good. But you can see the idea. Can somebody tell me why it doesn't work that well? Because the idea of eigenvectors, you know, you have a system, you can always decompose it in eigenvectors. So you have similar systems, right? It should work. Why does it perform that bad? So the main difference with the pictures, you think about it, the pictures, the ones that we used right now was 50 by 50, right? So that's 2,500 features. So that means it's a space of 2,500 dimensional space. And our data was 20, right? So you can see the difference, right? In this case, we have 30, and we have around 500, right? So what happens there is that, like, imagine now if I only have one dimension, and then I have a lot of points in those dimensions, right? So they're gonna, and I only restrict them from 0 to 255. I clock them, right? So they're gonna be very close together. Then when I send them my sample, well, of course it's gonna fail, right? But I can assure you, if you find a sample that has a lot of features and not so many examples, it will perform much better because of this reason. Because then you have a high dimensional space, and then these points will kind of cluster in the correct way, and then it will perform better. And that's why, at least in my opinion, it's not performing their best. And now, yep, I guess, thank you. And that's it.
So give them a